Okay, so in the previous class we just had a very quick overview or review of what you saw in your probability course. Uh, Today we'll get into something hopefully, so parts of which you've already seen in your probability course. We'll start with the basic concentration inequalities. But hopefully we'll also see some applications of these concentration inequalities to some problems in computer science. Okay, so before we actually get into concentration inequalities, we'll see one final tool that will be useful to prove some of the results that we have. So this is called Jensen's inequality, and it basically says the following. So if you have a convex function f, right? So f is a function over the reals, which is convex. Now you may have seen different definitions of convexity. So the commonly used definition is that so f is a convex function if for every pair of points x1 comma x2 in R, and for every alpha between 0 and 1, f of alpha x1 plus 1 minus alpha x2 is less than or equal to alpha times f of x1 plus 1 minus alpha f of x2. Now this is sort of the analytical definition, but it has a very intuitive interpretation. It basically says the following. So if you take any 2 points, x1 comma x2, on the real line, so let's call this x1, and this is my x2. This is what you evaluate at this particular point is f of x1. So this is x1 comma f of x1. And at this particular point, I have this point is x2 comma f of x2. Now, as I vary alpha between 0 and 1, if you think of the secant joining these 2 points, or the straight line joining these 2 points, any point along this line, right, if I take this particular point, this can be written as, or the y value is basically alpha. So this point essentially corresponds to alpha x1 plus 1 minus alpha x2 comma alpha f of x1 plus 1 minus alpha f of x2. Right. So any point on the secant can be represented as in this particular form. So the y value is just alpha times f of x1 plus 1 minus alpha times f of x2. Right. So that's some point along this particular straight line. And now I also have alpha times, f of alpha x1 plus 1 minus alpha x2. So alpha x1 plus 1 minus alpha x2 is going to be this particular point, right? And the value of f at this particular point x, which is equal to alpha x1 plus 1 minus alpha x2, which is this point over here, that's the left hand side. So what this definition is basically telling us is that the curve that defines the function always lies below the secant. So if you take any 2 points along this curve, then the straight line joining these 2 points always lies above the curve that defines the function. Right? So that's the geometric interpretation of convexity. This can be generalized to higher dimensions, of course. So that's the definition of convexity. But one way to test for convexity, that's something you may have seen in high school, is that if f is twice differentiable, then f is convex if the second derivative of f at any point x is less than 0 or greater than 0. Right? So take an example of a convex function. What's the most common example you can think of? f of x is equal to x square, what is the second derivative? Which is positive, right? So the function is convex. Any twice differentiable function is convex only if the second derivative is greater than or equal to 0 at all points. And again, what is the geometric interpretation of this particular statement?
So the tangent keeps on, the slope keeps on increasing.
Correct. So the slope keeps increasing, right? So, and you can see in this particular example over here. So if I take any 2 points, let's take this particular point on the left, and I draw the tangent, right? This corresponds to a certain slope. If I go towards the right, you see that the slope keeps increasing, right? And that's what this particular statement is trying to say. The slope has to keep increasing, right? So these are two different. There are a number of other interpretations and properties of convex functions, but these are perhaps the most important that you need to keep in mind. Similarly, we'll say that a function is concave if minus f is convex. All right? So a convex function looks somewhat like a bowl, right? And a concave function looks like an inverted bowl. So minus f. Right? What will be useful for us is this particular result, which is called Jensen's inequality. So if you have any convex function f on R, and x is some random variable, then f of expectation of x is always less than or equal to expectation of f of x. Right? And in fact, if you just, let's suppose that x can take only 2 values. X is a random variable that takes only 2 values. Let's say x1 with probability alpha and x2 with probability 1 minus alpha. Then you can see that what I have over here is exactly the definition of convexity. Right? What is expectation of x? If x is a random variable that takes x1 with probability alpha and x2 with probability 1 minus alpha.
Alpha x1 plus 1 minus alpha x2.
Exactly. So expectation of x is nothing but alpha x1 plus 1 minus alpha times x2. And what is expectation of f of x? It's just alpha f of x1 plus 1 minus alpha f of x2. Because alpha is the probability with which you get x1 and 1 minus alpha is the probability with which you get x2. All right? So in that sense, you can think of this statement as a generalization of this particular statement. Now, it's very easy to just directly derive this for discrete random variables. Just by going by the definition of convexity. It takes a little more effort to prove this for continuous random variables, but I won't get into it. You can easily find a proof. If possible, I'll maybe just give a proof on Google Classroom. But this is a useful tool in probability that comes up every so often. All right. Okay. Any questions so far? All right. Okay, so let's start with some of the basic tail bounds. You may have already seen these before, but nevertheless, we'll just prove everything from scratch. Okay, so we'll start with Markov's inequality, and maybe you can help me over here. So what does Markov's inequality say? So we start with a random variable x, and the expectation of x is some value mu, which we assume is finite. Do I need any other properties on x for Markov's inequality? Yeah. Yeah. So x has to be a non-negative random variable. So x is greater than or equal to 0 with probability 1. So the probability that x is less than 0 is equal to 0. So I'll use this. You'll see this very commonly with probability 1. Right? This means that some property is satisfied with probability exactly equal to 1. Right? So if this is the case, then what can you say? What is the probability that, so let's fix an arbitrary delta greater than 0, the probability that x is greater than or equal to delta is less than or equal to, so it's less than or equal to mu by delta. And how do you prove this particular statement? So let's start with the definition of the expectation. So mu, right? What is mu equal to? For now, just for convenience, so that notation is simple, we'll assume that x is a continuous random variable with a valid probability density function. You can generalize this, but just to keep notation simple, let's assume that's the case. So what is the mean mu equal to? Again, I can simplify it much further, because what do I have? What are the assumptions on x? X is non-negative, so the range is only from 0 to possibly all the way up to infinity. All right. So what is the mean equal to? So it's equal to integral from 0 to infinity of x times fx of x dx. All right. Good. So this, I can split this integral into two parts. Right? One that goes from 0 to delta, and the other that goes from delta to plus infinity. So this is integral from 0 to delta x times fx of x dx plus integral from delta to infinity x times fx of x dx. Right, nothing fancy so far. Now, ultimately, what do I want? I want to, so if you think about how the inequalities should go, I want mu to be, so this statement over here, the statement of Markov's inequality, if I rearrange, basically I should get mu greater than or equal to delta times probability that x is greater than or equal to delta. All right. This is an instance where we know what the final result is. So we have somehow to get this. Right. So if I look at the second term over here, right. So for every so within this particular integral, x is always greater than or equal to delta. So this quantity is greater than or equal to delta times integral from delta to infinity fx of x dx. So then I would get delta times probability that x is greater than or equal to delta. This is the only term that is unnecessary, but what I know is that this quantity is greater than or equal to 0. Right, the first term is greater than or equal to 0. The first term is greater than or equal to 0. So this quantity is greater than or equal to 0 plus integral from delta to infinity. Within this integral, x is always greater than or equal to delta. So this is greater than or equal to delta times fx of x dx. If I take delta outside, then I get integral from delta to infinity fx of x dx. But what is that equal to? That's just probability that x is greater than or equal to delta. This is exactly what we were looking for. Right? Are there any questions?
So in which case is that equality holds, like probability of x greater than equal to delta
Mm-hmm.
is equal to mu by delta.
Is equal to mu by delta. Okay, so if this had to happen, let's say for a particular delta, all right, what do you think should happen? So where do we have the inequalities?
First term that we are breaking, if that goes to 0,
So that should essentially be equal to 0, right? If I want if I want this Markov's inequality to hold with equality, then the first term should be equal to 0, and the second term should be exactly delta times probability that x is greater than or equal to delta.
that means like for every x greater than delta, like the value that x is taking is delta only.
Not necessarily. So, for example, let's assume that x is equal to some particular value with probability 1. Let's say x is equal to 1 with probability 1. Then what would I get? What is mu?
X is
So the particular example that I have in mind is right. So x is equal to 1 with probability 1. Right. So what is expectation of x? Okay, great. It's equal to 1. Let me say that I also take delta equal to 1. Then you would get, what is the probability that x is greater than or equal to 1?
1 by 1 by.
That's 1. Right. So this is one particular instance. You can come up with multiple such instances, multiple such examples where Markov's inequality holds with equality. Right. But that's a good point. It means that in general, if we have no other assumptions on x or delta, then you can't really improve this bound. If you want a statement, an inequality that holds for arbitrary non-negative random variables with finite mean, then it is impossible to improve upon Markov's inequality. That's quite important. Okay, so now that we have a result for non-negative random variables, let's also try to derive something for arbitrary random variables. All right, let's suppose that x is a random variable with finite mean and variance. It's the only requirement I have. The expected value of x is equal to mu, which we assume is less than infinity. Could be positive, negative, doesn't matter. And the variance of x is sigma square, which is also less than infinity. Right? Higher order moments may or may not exist. Then, for all delta greater than 0, the probability that x deviates from the mean by an amount delta is less than or equal to, yeah, just 1 by delta square. So it's sigma square by delta square. Right? So obviously, so it's also useful to think about these bounds. So these are what we call tail bounds. So it's good to keep a picture in mind. So let's say that I have some random variable with whatever, some PDF. Right? So this is my fx of x. Let's assume that the mean, this is my mean. Now if I fix a particular delta greater than 0, what is the event mod x minus mu greater than delta correspond to?
So we are looking delta positive of mu and delta negative of mu, like that interval.
Alright, so you have some interval of width, say 2 delta. So delta to the left of mu and delta to the right of mu. So what we are asking for is what is the probability that the random variable x lies outside this particular interval. Right? Now what does that correspond to in terms of the probability density function? It's basically the area under the curve under the probability density function to the right of mu plus delta and to the left of mu minus delta. Right? So the total area under the probability density function in the region from mu plus delta to infinity and minus infinity to mu minus delta, that is the quantity of interest. Right? That's the probability that we're interested in. And you should try to develop some intuition as to how this should behave. Right? For the same value of mu and delta, if the variance is larger, right? If the variance is larger, what does it mean? The probability density function is kind of wider, it's fatter, right? If sigma square is small, if the variance is small, then it's going to be more pointed and narrower, right? Which would mean that if sigma square is small, then the area under in this particular region would be smaller. For the same mean, if I just reduce the variance, then the PDF would become more pointed, so that the area under the tail would basically reduce, the tail probability would reduce. So it's natural to expect that this probability, the tail probability, should be larger if sigma square is larger and should be smaller if sigma square is small. Right? That's some intuition it's good to develop this. Okay, so how do we prove this?
We take x, y is equal to x minus mu whole square as another random variable.
Sure. So
Markov inequality.
exactly. So it's nothing but just a corollary of Markov's inequality. Right? You have this particular probability. Greater than delta. This is equal to, since mod x minus mu is non-negative, delta is also greater than 0. This is equal to x minus mu the whole square greater than or equal to delta square. Now I can take x minus mu the whole square to be a random variable. So y is equal to x minus mu the whole square. This is a non-negative random variable. And I apply Markov's inequality. I get this is less than or equal to the expected value of y divided by delta square. But what is expected value of y? Exactly. So it's x minus mu the whole square divided by delta square. which is nothing but the variance of x divided by delta square.
Sir, one doubt, sir. Why are we interested in that area's probability being bounded?
Okay, so one thing is that we want to understand for a single random variable, right? For an arbitrary random variable x, this is perhaps, this is useful in certain applications, but the kind of applications that we're interested in is when this x is maybe a function of many random variables, right? So let's take a very specific example. So suppose that I have n IID random variables, x1, x2, up to xn, which are all IID, drawn according to some distribution, discrete or continuous, doesn't matter. But we'll assume that the mean of x is mu, right, which is finite. Okay. The quantity of interest is this random variable, let me call this an, which is 1 by n summation I equal to 1 to n xi. So for instance, if x1, x2, x3 are the outcomes of the toss of, let's say, a fair coin, and I map this to random variable, so it basically corresponds to a Bernoulli random variable. The probability of getting 1, so 1 corresponds to a head and 0 corresponds to a tail. Then an corresponds to the fraction of heads that I get in n coin tosses. Right? So what you've already seen is that in a basic probability course is that as n becomes larger and larger, as n tends to infinity, what does this tend to? The half in the case of the coin tossing experiment, but in general it's going to converge to the mean mu. Right? So the weak law of large numbers basically tells you that an converges to mu in probability. Right? The exact definition of the statement is basically the weak law of large numbers. What it says is that for every epsilon greater than 0, the probability that an minus mu is greater than epsilon tends to 0 as n tends to infinity. This is the precise statement of the weak law of large numbers. So this is what we know, and this is, in fact, our intuition says that this should be true. Although this says that eventually it must go down to 0, it doesn't tell us how fast it must go down to 0. Right? Which is important to us in a number of applications. We'll see some specific examples to see how this can be applied, but to be more concrete, the goal is to find out at what rate does this probability go down to 0. Right? That will be the main focus of this entire course. For different classes of random variables, and this an could be something different. It need not necessarily just be an average. Right? So tools like the weak law of large numbers or the central limit theorem tell us something about the asymptotics. As n tends to infinity, certain probabilities converge to something. But we are interested in knowing how fast this convergence happens. Also, we may be interested in what happens for small n. Let's say n equal to 3 or 4. I want a result that holds true for every single n. Although it may become useful for large n, I still want to know exactly what happens for n equal to 2, 3, 4, 5, everything. Okay, so let's maybe go ahead with this very specific example. and try to use Chebyshev's inequality on an. So I want to know at what rate does this probability go down to 0. Okay, so what do I need? What is expected value of an? It's equal to mu. And what is the variance of an? It's sigma square by n. So the simple reason is this is equal to the variance of 1 by n summation I equal to 1 to n xi. If you have IID random variables, then the variance of the sum is equal to the sum of the variances, and the variance of some alpha times a random variable x is alpha square times the variance of x. So this is 1 by n squared times the sum of the variances of the xi's. But the variance of xi is sigma square, so I get n times sigma square in the numerator and an n square in the denominator. This is nothing but sigma square by n. Mind you, I can do all of this only if the xi's are independent and identically distributed. Right? At the very least, you can verify it that at the very least I need pairwise independence between xi and xj for every ij. Okay, so now I know the mean of an, I know the variance of an. My goal was to bound probability an deviates from mu by an amount epsilon. What does Chebyshev's inequality tell us? So this is less than or equal to sigma square by n divided by epsilon square. Right? So basically this tells us that this converges to 0 as n tends to infinity at a rate of 1 by n.
Since n will be fixed for a particular series, let's say that we are taking that is number of instances.
Okay.
So 1 by n will be a like fixed number, so we can say that this is decreasing to 0 with linear rate.
So we fix sigma square and we fix epsilon, and you're letting n to grow unbounded. Right? You keep continuing your coin tosses on and on and on. So if you keep continuing your coin tosses, then it is as a function of n, this decays to 0 at an inverse at a 1 by n rate. All right. Any questions? So some points to be kept in mind. So one, this holds true for any distribution with finite mean and variance. We did not require any other assumptions on the random variables xi. Right? So this may not be the best possible rate of convergence for specific distributions. It's possible that for certain distributions, this convergence happens much faster. Right? For specific. And that's because we didn't make any other assumptions on the distribution. It's anything with a finite mean and variance. Right? The second point is regarding the weak law of large numbers itself. In fact, the weak law of large numbers holds even if the variance is not finite. So in that sense, I agree. So this what we proved over here is exactly the weak law of large numbers. But this is the weak law of large numbers, assuming that the variance is finite. But in fact, in general, the weak law of large numbers holds even if sigma square is not finite. Right? And you can generalize it even further, but even if sigma square is not finite. All right. Any questions? Okay, great. So far, Chebyshev's inequality gives us some bound on the trail probability, but as we've seen, the bounds aren't great. You will always get a polynomially decaying bound. In fact, if you think about it, you could generalize Chebyshev's inequality a little more, because what was the trick that we used? We started with, ultimately, what was our goal? Our goal was to bound this particular probability, right? Under the assumption that the second moment is finite, that is sigma square is finite. And for this, we took this particular quantity, we raised both sides by the power 2, and then applied Markov's inequality. Now let us suppose that higher moments also existed. Then there's nothing sacred about 2, right? In principle, I could have raised both sides to the 4th power, right? Then I would get probability x minus mu the whole power 4 greater than or equal to delta to the power 4. And again, I could just apply Markov's inequality on that. And then I would get the 4th moment divided by delta to the power 4. All right. In general, I can just say that probability that mod x minus mu greater than or equal to delta is going to be less than or equal to, let's say, the 2kth moment divided by delta to the power 2k. That's a very easy, it's a simple generalization of the Chebyshev's inequality that I get as long as higher order moments exist.
Is it always better if you have power 4?
In fact, you in general you will get better bounds if the higher order moments are bounded. Again, it's perhaps not directly evident over here, but the running example that we want to keep in mind is the random variable an, right? And how this varies as a function of n. Okay, so think of n to be something very large. All right, so simple. Let me do that carefully. Oops. So simple generalization is that the probability that mod x minus mu greater than or equal to some delta is going to be less than or equal to expectation of x minus mu whole to the power 2k divided by delta to the power 2k. Okay. Now if my x corresponds to an, then this particular approach greater than or equal to delta would basically give me some constant divided by n to the power, not just square into the 2k minus 1. That's what one would expect. So I can get a higher order polynomial by taking higher order moments. Alright. Assuming that I had IID, so AN is just the average of n IID random variables. So what I want to say is basically that not this is an advantage, it's still a limitation. No matter what I do using this particular approach, at best I can get a polynomial decay as a function of n. In fact, it turns out for many classes of random variables that we're interested in, we can in fact get an exponential rate of decay. So my
If you take the second moment, it will be like it decays at the rate of 1 by n.
correct.
So like if we generalize it, then if we take a to be large,
Yes.
then the 1 by n power 2k minus 1 will become small. So then
Correct.
the convergence rate will be like,
Faster than 1 by n, right?
so like it can be even 10 into 0.
What do you mean 10 into 0?
So like n power 2k minus 1 will increase.
Correct.
So the 1 by n power 2k minus 1 all the term will decrease.
Correct.
So like it can become as small as possible.
Correct. So in general, you can choose a higher and a larger k to get a faster
How
decay.
can we derive from more strict ones? Like if it is as small as possible, then what is the use of it? Like,
Because we want to prove the tightest rate of decay. Right. Again, the actual rate at which it decays is a property of the random variable. Right. This 1 by n to the power 2k plus 1 or 1 by n or 1 by n square, it's an artifact of this particular technique that we use to derive the bound and the assumptions we use to derive this particular bound. Okay. Now, suppose that all of the moments exist. Let's assume that we're in that particular scenario. Then I could choose an arbitrary k because I know that all moments exist. Which means that this probability decays as 1 by order 1 by n to the power k for any k greater than 0. But that's still a polynomial decay. Alright. What I want, in fact, for such random variables, we can prove an exponential rate of decay, which Chebyshev's inequality doesn't give us. And that's mainly because we use this particular technique of raising both sides to the power k and then using Markov's inequality. Right. So that's the point. We'll use essentially the same approach, but a slightly more clever trick. Instead of raising both sides to the power k, we'll take the exponential on both sides, and that automatically just gives us an exponential rate of decay. Any other questions? Okay, so we'll now look at the Chernoff bounds, sometimes called the Kramer-Chernoff bounds. So this basically gives us not just one bound, but in fact a family of bounds. And much of what we'll see, at least what we'll see for the first part of this course, essentially involves manipulating the Chernoff bound into a more usable form. Okay. So we'll assume that x is a random variable with a well-defined moment generating function. Let's call this phi x. All right. For the moment generating function to exist in a neighborhood of 0, then all the moments have to exist. All right. So we're remember that Chebyshev's inequality only required the second moment to be finite. Markov's inequality did not even require that. It required the non-negativity constraint, but otherwise we didn't assume that even the variance exists. But now we are imposing much more stronger restrictions that all of the moments should exist. So x is a random variable with moment generating function phi x. Then for all delta greater than 0, we'll look at two different cases, the left tail and the right tail. Right? Earlier in Chebyshev's inequality, we were just interested in what is the probability that x minus mu is either to the left, or x is either to the left of mu minus delta or to the right of mu plus delta. And now we look at these two tails separately. The probability that x minus mu is greater than or equal to delta is less than or equal to phi x of t divided by e raised to t times delta plus mu, and this holds for all t greater than 0. So the bound has a parameter t, which has to be positive, but each value of t gives you a different bound. So some values of t may give you a very weak bound, some values of t may give you a reasonable bound. Similarly, I can bound the left tail, x minus mu is less than or equal to minus delta is less than or equal to phi x of minus t divided by e raised to t times delta minus mu. Again, all of this holds for t greater than 0. So I'll only prove the first part of the Chernoff bound for that is the right tail probability that x minus mu greater than or equal to delta. So just a word regarding convention, this is called the right tail probability and this is called the left tail. Right, so if you have that picture of the density in the mind, you are interested in this is some random variable, this is mu, this is mu plus delta, mu minus delta, and this corresponds to the right tail probability, whereas this corresponds to the left tail probability. The idea is simple. You just start with probability that x minus mu is greater than or equal to delta, and you just take e to the power on both sides. This is equal to probability that e raised to x minus mu, or let's perhaps do it one step at a time. This is equal to the probability that t times x minus mu is greater than or equal to t times delta for any t greater than 0. Right? These two events are exactly the same. And since the exponential function is monotonically increasing, this is equal to the probability that e raised to t times x minus mu is greater than or equal to e raised to t times delta. As the exponential function is an increasing function. Now, all I have to do is just apply Markov's inequality. So this is less than or equal to e raised to expectation of e raised to t times x minus mu divided by e raised to t times delta, right? Or maybe just simpler would have been, I could have just manipulated this probability that e raised to t times x is greater than or equal to e raised to t times mu plus delta, and now I can apply Markov's inequality with expectation of e to the power t times x divided by e raised to t times mu plus delta, which is nothing but the moment generating function divided by e raised to t times mu plus delta. Any questions?
So, sir, here we are trying to minimize the area that is.
No, we're not trying to minimize the area, right? So the area is something that is fixed, which depends on the distribution. Whatever we are trying to do is get a bound on this particular area, right? And our goal is to derive the tightest possible bound under this. No, okay, why are we going through these specific bounds? Now, if I give you a particular distribution, you could try to compute the area under the curve in this particular region. Right? You evaluate the integral from mu plus delta to infinity of fx of x dx. That's one way you could go about. But then you would have to do this for every single distribution you want. If this distribution is simple, then maybe you could just compute this directly. That will give you the best possible bound, obviously. But then you don't want, sometimes the distribution itself may be complicated, so evaluating this integral could be hard. And sometimes you don't know exactly what the distribution is, you only know some properties of it. So in these cases, this becomes useful. Right?
So that we have a bound on area.
Correct. You get a bound on the area under the curve. So, for example, it's slightly more obvious with the Chebyshev's inequality. Right? So this statement that this bound that I had sigma square by n epsilon square, for example, I didn't need to know what the exact distribution is. All I needed to know was that the variance is finite. In fact, if I'm only interested in very large n, I don't even need to know what the value of the variance is, because I automatically get at what rate it will decay. All I need to know is that the variance is finite. Right? So the idea is to derive bounds with the minimal set of assumptions. So if I make certain assumptions on the distribution, nothing else, I don't even need to know the specific form of the distribution, then what can I get? All right. And as we'll see, it becomes more complicated, right? So the random variable a, let's suppose that a is Bernoulli, x is Bernoulli. I know exactly what the distribution of x is. But then what about an, which is an average of Bernoullis? For this case, it's going to be a binomial, right? And I could still do something for the binomial. But there could be more complicated distributions. Right? And even for the binomial, the exact expression for the tail could be very complicated. It's going to be in terms of binomial coefficients, and it's going to involve a huge sum of binomial coefficients, which is difficult to evaluate because in the end we may only be interested in deriving bounds. All I'm interested in is knowing at what rate does it decay. All right? And many of these bounds are reasonably good enough. Okay, so I've posted homework on Google Classroom wherein you will derive the mean, variance, and the moment generating function for some common random variables, right? So, and we'll be using some of these in the course. And as you've seen, the moment generating function also allows you to get tail bounds on the probability of those classes of random variables. So what we derived right now is for a single random variable. But again, as I said, we'll have this example always running throughout the course. That is, an is equal to 1 by n times summation I equal to 1 to n xi, where the xi's are IID random variables. We'll also sometimes look at Sn, which is just the sum, I equal to 1 to n xi. Our goal will be to derive tail bounds on an. If I can derive tail bounds on Sn, then they're both equivalent. Right. We've seen previously that the variance of an is 1 by n times sigma square, and the variance of Sn is n times sigma square. So what about the moment generating function of an, or moment generating function of Sn? This is expectation of e raised to t times Sn, which is nothing but expectation of e raised to t. In fact, let me do this for an itself in one go. T times an, which is t by n times summation I equal to 1 to n xi. Right? Can I simplify this? So this is I want to derive the moment generating function, or an expression for the moment generating function of an in terms of the moment generating function of x, because that's something that I know. What can I do with this?
So we can send the expectation like on top of exponent, like e to the.
Why you can't do that?
So e into x, we can then make it expectation of e into e raised to t by n xi, and then whole raised to n. Yeah.
Sure, let's go step by step. So firstly, I have exponential of a sum, so I can write that as a product of exponentials. Right? This is equal to expectation of the product I equal to 1 to n e raised to t by n xi. Right? Now what do I know about the random variables xi's? They're all independent. Right? So if the xi's are independent, then e raised to t by n xi's, they're also independent. Right? So this quantity over here, if I denote this yi, then the yi's are also independent and identically distributed, because it's just a function of xi. So what is the expectation of a product of IID random variables? It's equal to the product of the expectations, and in fact, so this is equal to product I equal to 1 to n, expectation of e raised to t xi by n, which is nothing but, I mean, all of the xi's are independent and they're also identically distributed. So this is equal to expectation of e raised to t times x divided by n whole to the power n, which is nothing but phi x of t by n whole to the power n. Okay, so in general, probability that an is greater than or equal to mu plus delta using the Chernoff bound, this is going to be less than or equal to phi x of t by n whole raised to the n divided by e raised to delta times t times mu plus delta. And similarly, probability that an is less than or equal to mu minus delta is going to be less than or equal to phi x of minus t by n whole raised to the n divided by e raised to t times delta minus mu. Right? And all of this holds true for every t greater than 0. Okay, so that's an advantage.
So why we introduce B?
It's something that comes out of the, so for every t I get a bound, and really what I want to do is choose that t which gives me the best bound.
So like in the proof we multiplied T
By T,
with
correct.
x minus mu at a particular step.
Correct.
So that was intentional so that we can like later on change T and get tighter bounds.
Correct. So because I got that additional flexibility of choosing whichever t I wanted. If I didn't, suppose in this particular step, over here if I didn't multiply by t, I would have got e to the power x minus mu greater than or equal to delta, right? Which in the end would have given me phi x of 1 divided by e raised to mu plus delta, right? Which may not be the best.
And T here will be constant, like
And t is going to be fixed, typically. Alright. Okay, so in fact you can try to simplify this for specific distributions, and we'll use one particular bound for the Bernoulli distribution. In fact, that's also a homework problem. So we'll use this bound frequently. So if x1, x2 and so on are IID Bernoulli P random variables, then the probability that an minus the mean is greater than or equal to some delta times the mean p is less than or equal to, there are two bounds, we'll use both. So 2 times e raised to minus n delta square p by 3. So this bound holds true only if delta is between 0 and 1. But it's also less than or equal to 2 times e raised to minus n delta square p divided by 2 plus delta, and this holds true for any delta greater than 0. Maybe we should. So it means that for, at least for the Bernoulli distribution, the probability that the fraction of heads is greater than some greater than p by an amount delta times p, that the fraction of heads deviates from the probability of getting a head by an amount delta p, decays exponentially in n. Using the Chebyshev and those type of inequalities, I could only show that it decays polynomially in n. But now I have an exponential bound. Alright. So let's immediately see a couple of examples or applications where this can be used. So we'll see a problem in that occurs in computer science, which is called load balancing.
So, excuse
Yeah.
why did we do delta p?
I mean, I could just have just delta, but this particular form is useful because it tells us that the probability that an is greater than, for example, an greater than or equal to p times 1 plus delta. In particular, when p itself, right now this is true for any p. We'll see examples where p itself could also be a function of n. Again, you could express this. So this is sometimes called a multiplicative form of the Chernoff bound. You could also just replace this by delta. And similarly, what you have over here would also change. It's not easy to go between the two different forms of the bound, but this kind of looks nicer because it tells you that this varies, this decays exponentially in delta square.
So is that delta greater than 0 or delta greater than 1? Second one.
The second one is true for every delta greater than 0. Even if delta is greater than 1, it still holds. But if delta is, so this is nothing but a slightly tighter form of this particular bound here, nothing else. Right? You can almost immediately see it. If delta is between 0 and 1, then 1 by 2 plus delta is going to be less than or equal to 1 by 3. It's going to be greater than or equal to 1 by 3. So this gives you a tighter bound and this will give you just a looser bound. The main difference between the two is that here I have a delta in the denominator, whereas here I don't have a delta in the denominator, so sometimes this is slightly easier to work with. That's it. Right. Again, this is not the tightest form of the Chernoff bound, even for Bernoulli random variables. Okay, so let's see one particular application. And the application is the following. It's a problem of allocating jobs to a server. It's a distributed computing setup. So I have n servers, server 1, server 2, server 3, and so on. I have n different servers, and I have jobs coming in sequentially. So job 1 up to, let's say, m jobs. You don't know beforehand how many jobs are going to come. And the problem in load balancing is to allocate these jobs to the servers such that no single server has too many jobs. Ideally, you want to allocate it in as uniform a manner as possible. So as and when jobs come, you want to allocate them to different servers. Right, so that's the goal. Now, given nothing else, perhaps the most natural way of distributing these jobs is to allocate the jobs in a round-robin fashion. Right? You get the first job, you allocate it to server 1. You get the second job, you allocate it to server 2, server 3, and so on. Right? Once you get more than n jobs, you again go back to server 1, server 2, and so on. So that's the round-robin fashion of allocation. Another, perhaps more natural way is to always allocate if you get a new incoming job, you allocate it to the server which has the fewest number of jobs that are currently running. Right? But all of these approaches requires you to know something about the state of the system. You need to know which server has how many jobs, and you also need, so that's for the second system where you allocate jobs to the server with the least amount of pending jobs. That's one. For that, you need to know how many jobs each server is currently running. If you want to do it in a round-robin fashion, you need to have a count, or you need to be able to keep track of how many jobs have already come in the past. Right? Or essentially, all of these require some kind of a central entity which is going to allocate jobs. Right? And this central entity is going to control which job goes to which particular server. In many applications, you can't really do this because jobs may come from different sources, and there could be no central controlling unit which decides to allocate which job to which server. So in the absence of such a central controlling unit, one approach is you get a new job, you just randomly allot one server to it. All right? So given a new job, allocate to a server that's uniformly at random chosen from the set of servers. So this does not require a central entity deciding which job has to go to which server. Some new job comes, it just gets allotted a random server. And the server processes these jobs in whatever fashion it wants. All right. This is very simple to implement. And in fact, some variant of this is actually implemented in practice. All right. So this is one particular form of allocation. Suppose you did the best form of allocation, all right, and you have m jobs and you allot to n servers in the most uniform possible, in the most balanced way possible. How many jobs should be allocated to each server? There are m jobs in general, m by n. Right? So in fact, if there are n jobs and n servers, exactly one job should be allocated to each server. Now, if I'm doing a completely uniform random allocation, this may not be the case. some jobs could potentially, so some servers could potentially get more jobs, too many jobs, and some servers may be completely vacant. All right. So our question is, if I do a perfectly random allocation, then what kind of can I derive bounds on the probability that one server has too many jobs? And what is a good bound on this? All right. So firstly, how do we model this particular problem? All right, using what we have already seen previously. So let's set up some notation. I'll define a random variable, chi ij. That is, it tells you which server got which job. So it's equal to 1 if the ith job is allotted to server J, and it's equal to 0 otherwise. Okay. So now so I have m times n random variables. Right? I can think of this as a matrix which tells you how the jobs were allocated to the different servers. So this chi I corresponds to the jobs. There are m jobs and n servers. So you can write this in the form of an m by n matrix. Sure. Right. Now if I look at this collection, let's look at one row and one column. Right? Any particular row, any particular column. What can I say about chi I1, chi I2, chi IN versus chi 1j, chi 2j, chi mj. Let's maybe start with this particular collection. What is the distribution of chi ij? So right now I have fixed a particular server, let's say server 1. This pick a particular job, the ith job. What is the probability that the ith job gets allotted to server 1? It is 1 by n, right? So I know that probability. So in other words, each chi ij is Bernoulli 1 by n. Okay. What about, let's fix server j. First job and the second job, are they independent of each other? They're all independent, right? Because each job is independently allocated to a particular server. Right? So chi 1j, chi 2j, and so on, all of these are IID. But can I say the same of chi I1, chi I2 up to chi IN? No, right? They are not independent. So for a given job, the server that this is allocated to, these are not independent. Because only one of them can be a 1, the rest of them have to be a 0. Because a job is allocated to only one server. Right? So these are not IID. Great. So now if I look at the load for server J, let's call it LJ. What is it in terms of the chi ij's? Can I write it in terms of the chi ij's? Correct. It's just sum of the chi ij's. 1, 2, I have m possible jobs. So it's just the sum of the chi-ij's. Right? So this is a useful trick. I mean, the underlying random variable was a bit complicated because you have a number of jobs, you have servers, you have this random allocation, but we expressed all of these as a sum of Bernoulli random variables. And this is a trick that you commonly use in many computer science applications, computer science, machine learning, many other such applications, where even though your actual random variables could be a bit complicated, the quantity of interest can sometimes be written as a sum of IID Bernoulli random variables, depending on what event that you want to look at. Okay, so the load for the server J is just a sum of IID Bernoulli random variables. What is the expected load? Each chi-ij is Bernoulli 1 by n. It's m by n, right? So that is good because that's a uniform, it's a balanced allocation. Okay, but this is only in expectation. It could deviate significantly from the expectation. But then it's not too bad because if n is sufficiently large, right? If m and n are reasonably large, then I know from my Chernoff bound that the probability of deviation is not too much because I have exponential tail bounds. Right? So, what is the probability that Lj, in fact, minus expectation of Lj, or the deviation is m by n, is greater than or equal to some m delta by n. Right, so again, I want to look at the case where delta could be arbitrary. Okay, delta need not necessarily be between 0 and 1. Okay, for this I can use the second Chernoff bound. Right, this particular expression that I have. So this is less than or equal to 2 times e to the minus n delta square p divided by 2 plus delta. So this would be m delta square. T is 1 by n whole divided by 2 plus delta.
Here we're dealing with summation, right? Not summation divided by m.
Good point.
We should take Lj by m.
That's still okay because the expectation would again be normalized, right? You're right. Let me try to express that in terms of 1 by m, or the probability that Lj divided by m minus 1 by n is greater than or equal to delta by n. This is what I would have, right? Which will essentially give me the same thing, right? Which is less than or equal to 2 times exponential of minus m delta square by p divided by 2 plus delta. All right. This is... Now I want to find out what is the probability, or what is the... Suppose that I want to target probability. All right. That is... I'll say that the load is at most m delta by n with high probability if this probability is at most 1 by n. Right. So for what values of delta is this at most 1 by n. So that gives me tight bounds on the maximum load that is present, assuming a certain probability guarantee. All right. So, in fact, so this is for one particular server J. Right. What I'm really interested in is what is the probability that Lj is greater than or equal to 1 plus m by n plus m delta by n for at least one j. Or in other words, what is the probability that all of the servers are reasonably balanced? So this is the probability that at least one server is kind of unbalanced. I'd say that a server is unbalanced if the load is greater than m by n plus m delta by n. Now I can use the union bound on this, because what is this? This is just the probability that union j equal to 1 to n, Lj is greater than or equal to m by n plus m delta by n. Right? And this by the union bound is summation j equal to 1 to n. Sorry, I should have. Yeah. In servers, probability that Lj is greater than or equal to m by n plus m delta by n. Note that the Ljs are not independent of each other. Right? That's something that you should keep at the back of your mind. But I can still use the union bound. This union bound may not be tight. And this is less than or equal to n times 2 times e to the power minus m delta square by n times 2 plus delta. Now we can show that this is going to be less than or equal to whatever, some constant by n if I choose delta to be equal to something that scales as log n. Alright. It's just a simple, it's an easy exercise to see this. So basically what this is saying is that with high probability, the maximum load on any server is going to be, let's take m equal to n. If m equal to n, then the max load is going to be less than or equal to 1 plus something times log n with high probability. When I say with high probability, the probability that this does not happen is decays as 1, at least as 1 over n. Alright, so there are n jobs. The max additional load that a particular server has to take is just something that scales as log n, which is not so bad. In fact, in practice, for example, in your AWS systems, what is implemented is a slight variant of this particular randomized allocation. What they do is, as soon as a job comes, you pick 2 servers uniformly at random. All right, pick any 2 servers, And then out of those two servers, you see which one has a lower load, and then allot to that. Alright. This turns out, if you do that, then it turns out that you can reduce this extra load from log n to log n, which decays much. It is much smaller. Alright. Okay, so I've gone over time, so let's stop here. Any questions?
Sir, for the AWS example that you gave,
Yeah.
since again it's checking that which of the two servers has less loads of
Correct. It requires some additional, but still it can be done in a completely decentralized fashion.
And so one more doubt, like this involves multiple servers,
Correct.
but let's say we are just dealing with one server, or in the previous example, we are just dealing with A and
Okay.
so why not we use the tightest bond instead of like studying all the bonds?
It turns out that even if you try to evaluate, like derive this as a take the binomial distribution and try to derive that, you don't get anything much better. This in fact is pretty tight. The constants may improve, but you can't really improve things significantly as a function of n.
So is there a condition that when we cannot use the tightest bond, or every time we can use tightest bond?
Not always, I agree. But in general, if you can get an exponential bound, then that's usually good enough.